the Earth's rotation on its axis and revolution around the Sun. This is actually a quote from chapter 40 of Tirthaji's book, and there's a list in there which is titled Solids, Trigonometry, Astronomy, etc. And then the heading just below that title includes these words: a few of the important and most interesting headings under which these subjects may be usefully sorted. And then he gives a list of 9 items, and the 6th one is this: the Earth's daily rotation on its own axis and her annual relation around the Sun. So here we're going to explore what this might mean. We don't really know, of course, what Tirthaji had in mind, but there's just some ideas, and it's based on an article I've written which you can find in my website vedicmaths.org. And here's a diagram borrowed from the internet which shows the Earth spinning on its axis and going around the Sun at the same time. And the axis is inclined, which makes the geometry really interesting. It's inclined at about 23 degrees to the vertical, to the plane of the Earth's orbit, which means that the Earth's equator, or the projection of the Earth's equator onto the sky, which is called the celestial equator, is at 23 degrees to the plane of the Earth's orbit. So we start with our horizon and the east point on it, and then there's the equator going up from there. The equator always goes through the east point. It rises to its greatest height due south and then comes down on the other side at the west point on the horizon. And for every observer on the Earth, the equator doesn't move. It's always there in the same position and going through the east point. Also, this angle here is 90 degrees minus your latitude. So if your latitude is, say, 50 degrees, then this angle here will be 40. So you know where the equator is. And the next thing is to locate, once you've located the equator, you want to locate the ecliptic. And the ecliptic is the plane of the Earth's orbit around the Sun, and as I mentioned, this is inclined at 23 degrees to the equator. So at some point the Sun is at some place there, say. The Sun is moving this way. And this point where the ecliptic and the equator meet is very important. It's the zero that's normally used in astronomy for astronomical positions and calculations. So that's important. It's given this special symbol, which is the symbol for the constellation Aries, and it's called the first point of Aries. And there's the 23-degree angle between the equator and the ecliptic. So our job is to first locate E, the east point on the horizon, should be easy, then locate Aries, and then from there find the Sun. So we begin by choosing a 0 point in space-time, which is actually when Aries and the Sun are both at the east point on the horizon, which happens at the vernal equinox, the spring equinox, which is around the 21st of March, and at 6 a.m. That's our 0 time, and that's the 0 point. So let's see how we're going to find Aries, the first point of Aries. Aries is subject to 2 motions. One is due to the Earth's daily rotation on its axis, and the other is due to the Earth's annual revolution around the Sun. The Earth's daily rotation, since the Earth does 360 degrees in a day, will be 15 degrees per hour. And so in t hours it will travel 15t degrees, where t is the number of hours elapsed since 6 a.m. For the annual revolution, it moves 1 degree per day because the Earth takes about 360 days to go around the Sun, and so that's 1 degree per day. So in n days it will travel n degrees, where n is the number of days elapsed since the equinox. So these 2 motions can be added because they are actually in opposite directions, and therefore Aries and the Sun will be getting further apart by the sum of those 2. So this is our formula. E Aries is 15t plus n. And to illustrate it, we can take an example. Where is Aries 50 days after the equinox at 10 a.m.? Well, there's our formula. T is the number of hours since 6 a.m., so that's 4 because this is at 10 a.m. And n is the days elapsed since the equinox, which we're told is 50. So we need 15 times 4 plus 50, which is 110. So that means that the angle from E to Aries is 110 degrees. Now if you're puzzled by actually showing that a line is of length 110 degrees, then just think what we're doing here. These are points on the sky, on the celestial sphere, and what we mean by the angle of 110 degrees is that from your eye to E and from your eye to Aries are two lines which are 110 degrees between them. The angle between them is 110 degrees. Now, we've practically finished really our main job, which is to find the Sun, because we know that it's 50 days after the equinox and the Sun travels a degree every day, so after 50 days it will have travelled 50 degrees. So this angle here is 50 degrees, and because we know this is 23 degrees here, this diagram is all known and we can locate the Sun from that. However, positions in astronomy are generally described in a different way. Very often it's the angle measured along here plus another angle perpendicular to it that takes you to the point you want to go to. To do that, we're going to look at triples and quadruples. So what is a triple? A triple is just a set of three numbers that describe the size of a right-angled triangle. So for this triangle here, which has got sides 4, 3, 5, and is right-angled, we describe it by this triple 4, 3, 5. So that's a triple. And we can have axes on there as well, because we can call this the x-axis and the y-axis. And then this is the point 4, 3. And that's going to be useful for us. Here's another triangle with an angle of 30 degrees. So there's the triple, dash 1, 2, and if an angle is involved, we put it before. So 30 degrees, dash 1, 2. And the dash we put in if we're not really interested in one of the sides or we don't know it for some reason, we can just put a dash there, and we'll be doing that. So that's also a triple. And quadruples are a sort of three-dimensional triple, and here's an example. They're composed of 4 right-angled triangles. It's a kind of pyramid. You've got the origin here, the x-axis, the y-axis, and then the z-axis perpendicular to the xy plane. And this pyramid is defined by the numbers 6, 3, 2, 7. 6 in the x direction, 3 in the y direction, 2 in the z direction, and then 7 is the distance of that point from the origin. So 6, 3, 2, 7 is an example of a quadruple, and in general, if x, y, z, r is a quadruple, then it must be that x squared plus y squared plus z squared equals r squared. So now we're going to go back to our problem and find what's called the right ascension and the declination. The right ascension is denoted by the letter alpha, right ascension, and the declination by the letter delta, declination. So given the 23 degrees, which is always fixed of course, and the 50 degrees, which we're taking as our example, we want to know what alpha and delta are. Well, here's the diagram we just had showing the quadruple. Now the observer is not shown on this diagram, it's where your eye is, but it is shown on this diagram, it's where the origin is, or the O if you like. And so there's the observer looking at the triangle Aries US, which is the triangle Aries US here. So the angle A is the angle between the x-axis, or the line to Aries, and the line to S. So here It's from your I to Aries and your I to S, which means the 50 degrees there. So they correspond. And I is the inclination of, well, basically it's the inclination of the plane O Aries S to the base plane in the XY plane, which is O Aries U. And that's our 23 degrees. So this is A, 50 degrees in this example, and this is I. And if you need to pause at any point and just think about this, make sure you see the connection between this triangle here and this quadruple here, and then it will probably help if you need to do that. Now alpha is this angle here. It's in the XY plane and it's between O Aries and OU. So here it's between Aries and U, so that's your alpha. And similarly the declination is between U and S, that's that angle there, between OU and OS. So our job is, given A and I, to find alpha and delta. Well, there's our 6327 example here, and we can notice that the angle A on this diagram is this one here, O Aries S, and as a triple that will be 6-7, which is this. So it's given by the outer elements of that quadruple. Similarly, the inclination I is given by the two inner elements, because there's I and it's in the triangle Aries US, which is 3-2 dash. 3-2 dash. Now let's take another look at the 6327 and see where alpha and delta come in. Alpha is actually given by these two numbers, because it's in the base plane there. It's the triangle O Aries U, and so it's 6-3 dash, like that. So these first two numbers in the quadruple define it, and similarly the last two numbers define delta. Delta is here, and so it's -7. Now this gives us a method which we can use over here on the left, because we're given A and I. That's the problem. We're given A and I, and we need to find alpha and delta. So given A and I as triples, we simply can slot these two numbers in between the 6 and 7 there to get this quadruple, and once we've got the quadruple, we simply take the first two numbers for alpha and the last two numbers for delta. So we need to get A and I as triples, and so by some method or other, not discussed here, we find a triple for 50 degrees, which can be this, so that's A, and then a triple for the 23 degrees, which is the 12, 5, 13, and that's I. Now we want to slot these two together in the same way as we did here. We put this 3-2 between the 6, 7. So you might think we can just put the 12, 5 in place of that 105, but actually that won't work, because as it stands these two triples are not compatible. Sad but true. It's because of these two numbers here. The 105 and the 13 correspond to the line S Aries there, which is where those two triangles meet, the A triangle and the I triangle. They've got to be the same in order to make a quadruple. So what we do to make them compatible is to multiply this one through by 13. Multiplying a triple by some number doesn't change the shape or the angle, so we multiply this one by 13 and this one by 105, and we get this and this. I've just put dashes here because I'm not interested in that. I just want the numbers corresponding to these ones here. So now, having done that, I simply slot these two numbers in between those two numbers, and there it is. That's a quadruple for the position of S. So I can find alpha being the first two elements and delta being the last two elements. In fact, astronomers often use what they call rectangular coordinates, which are just these numbers here. And these also define the position, and you don't have to find alpha and delta in that case. You simply use those numbers, rectangular coordinates. So that's how it works. So we can find the Sun's position in these three steps. We find the east point first, then we measure 15t plus n degrees along the equator to find Aries. And then we measure n degrees along the ecliptic to locate the Sun. And if required, we can use triple and quadruple geometry to obtain the equatorial rectangular coordinates or the right ascension and declination. So here's the link to my paper on the internet. Thank you.